In the last video, we talked about how to calculate the vertical and horizontal asymptotes of rational functions. In particular, we saw that when the degree of the numerator of a rational function is less than or equal to the degree of the denominator, the graph of the rational function will have a horizontal asymptote, either at the x-axis or at a y level determined by the ratios of the leading coefficients of the numerator and denominator. However, when the degree of the numerator is larger than the degree of the denominator, we don't have a horizontal asymptote. However, if the degree of the numerator is just one larger than the degree of the denominator, we do get a kind of asymptote called a slant asymptote. So, recall from last time that if f of x equals p of x over q of x is a rational function, and the degree of p of x is equal to the degree of q of x plus 1, then f of x has a slant asymptote. Now, what this looks like in practice is that when we go to graph the function, we may have some vertical asymptotes. Let me give us a function with a vertical asymptote over here, but it won't have a horizontal asymptote. It will have what's called a slant asymptote, which will be given by a line, but one that is slanted. And what the graphs of functions that have slant asymptotes look like are something like the following. Here's an example. In red is the graph of the function f of x. And then on the other side, maybe it looks something like this. So what having a slant asymptote means is that our end behavior looks like a line of some non-zero slope. It means that as we move far to the right or to the left, the graph of our function gets closer and closer to some line. So a function f with a slant asymptote, which is written in the equation form y equals mx plus b, because it's a line with non-zero slope. A function with a slant asymptote of y equals mx plus b has a graph that gets closer to the graph of y equals mx plus b as x goes to infinity or x goes to negative infinity. As we move farther and farther to the right or the left, the graph of the function f looks more and more like the graph of the line y equals mx plus b. So the question becomes, how do we find this line? Finding horizontal asymptotes when they exist is fairly easy. The asymptote is just y equals 0 or y equals the ratio of the leading coefficients, depending on the relative degrees of the numerator and denominator. But finding a slant asymptote in the case where a function has a slant asymptote requires a more involved technique. And that technique is called long division of polynomials. So recall from when you were first learning about division, we have the following. We'll have some numbers a and b, and then when we divide a divided by b, what we often looked at are things like the quotient and the remainder. So we'll get a quotient q and remainder r, And we would wind up writing that A divided by B is equal to Q plus the remainder over B. Let's do a very quick reminder of how that works, both just to get it back in our minds, and because the technique that we use for long division of numbers is reminiscent of the technique we use for dividing polynomials. So for example, if we want to divide the number 2397 by the number 16, well, we would go through and start looking at the numbers in the dividend and say, all right, well, how many times does 16 go into 2? Well, it doesn't go into 2, so we move on. We ask how many times does 16 go into 29? It goes in once. And so here we say that by putting a 1 in this position over the 29, we say that 16 goes once into 29. So then we multiply and bring that down to this position here. Then, vitally, we subtract. And 29 minus 16 is 13. And then we bring down the next digit. In fact, it actually works in the process to bring down all remaining digits, although we don't often do that, but I will for this example so that we can compare it to what we're going to do with polynomials. Next, we say, all right, well, how many times does 16 go into 1? It doesn't. How many times does it go into 13? It doesn't. How many times does it go into 133? And it turns out that it goes into 133 8 times. So we put an 8 over the last digit that we had there. And we say, all right, well, 8 times 16 is, let's see, 8 times 10 is 80, 6 times 8 is 48, so this is going to be 128. And once again, we are multiplying and bringing down into position. We'll subtract again, and 133 minus 128 gives us 5. So we get 57. One last time, 16 goes into 57 3 times. We go 3 times 16 is 48. Let me shift this up. We subtract 48, and we're left with 9. So remember that we can continue this and get decimal places, but when you first encountered division, you probably stopped here and you asked what's the quotient and what's the remainder, and those two numbers can be read off from this diagram. The 183 is the quotient. The 9 is the remainder. The idea behind this is that 16 goes into 2,397 evenly exactly 183 times. And if you remove 16 from 2,937 183 times, then you'll be left with 9 left over. And so we can say that 2,397 is equal to 183 times 16 plus 9. And that's really what the division algorithm tells us. It tells us how to write down the dividend in terms of the divisor, giving us the quotient and the remainder. Now, the way that we often go from here is we divide both sides by 16. So we just go ahead and divide everything by 16. And we say, well, if we want to divide 2,397 by 16, the result of that is 183, because these 16s cancel, plus 9 over 16. And we often in elementary school would write this as 183 and 9/16 as a mixed fraction, but mixed fractions are not useful for algebra, so we've dropped them. But this is the idea. The division algorithm allows us to write a big number like 2937 in terms of a multiple of a smaller number plus some remainder. This is the basic idea behind long division of numbers, and it turns out we can do the same thing with polynomials. It's possible to express polynomials in terms of other ones using quotients and remainders. Now, these quotients and remainders are also polynomials. So, given polynomials, let me write them as a of x and b of x for comparison with what we just did. There always exists a quotient q of x and remainder r of x such that two things happen. First, a of x is equal to b of x times q of x plus r of x. So a and b have the same relationship with each other using this quotient and remainder as the numbers a and b did in the example we just did. And vitally, the degree of the remainder, which is a polynomial, is strictly less than the degree of b. Now, where this comes from is, in the previous example, we didn't talk about this explicitly, but the remainder, when you do long division of numbers, it will always be less than the divisor. We got 9 here, which is less than 16. No matter what remainder we get out of this process, it will always be less than the divisor that we started with when we were working on the algorithm. Thus, we get a similar result when we do long division of polynomials. And it's going to turn out that this is very, very useful to us. It's going to allow us to express quotients of polynomials in useful ways, or rather ratios of polynomials in useful ways, which are precisely the rational functions that we're talking about. So let's see how long division of polynomials works. So let's look at the long division of polynomials. And the best way to do this, in my opinion, is just to start with an example that will illustrate the techniques that we use. It's going to follow most of the same steps as long division of numbers do, but we'll be working with polynomials rather than numbers. So, example. Let's divide 2x to the fifth plus 10x to the fourth minus x squared plus 12 by x cubed plus x plus 1. So let's see how we set it up. We're actually going to set it up very similarly to how we set up the tableau for numbers. We're going to set up this division box right here, and inside the box is going to go the dividend. So this is the polynomial that you are dividing. So that's going to look like 2x to the fifth plus 10x to the fourth. Now, this is important. When we're working with numbers, sometimes one of our digits is 0, and that means that we have no tens, for instance, in our number. A 0 when we write out a number indicates that there are there's nothing in the tens place or the hundreds place or whatever. We also have to take that into account when we're working with polynomials. So in this case, notice that we've got an x to the fifth part, an x to the fourth part, but there's no x cubed in the dividend that we're working with. In order to keep everything in the right place, we need to include that in the dividend. So because there was no x cubed term in the original, we have to include it here. So I'm going to make notes as we go through this to help out. So we must include the missing terms in the dividend. And so that the terms of the dividend in our tableau go down by 1 degree each time. So plus 0x cubed minus, we do have an x squared term. We don't have an x term, so we need to include that as well. And then plus 12. And so we've got 2 missing terms in our dividend here. Next, we're going to put our divisor on the other side. X cubed plus x plus 1. Oh, my apologies. I needed to make this a 4x cubed plus x plus 1. Notice that we don't need the missing terms in the divisor. So we need to make sure that we write out the missing terms of the dividend, but we don't have to in the divisor. So this is the setup. And another thing I recommend that you do, especially your first few times going through this process, is to make some columns like this on your paper. And what that's going to do is it's going to separate your paper into columns, each of which correspond to a particular power of x. All of your x to the fifth terms will go in the first column, x to the fourth in the second, and so forth and so on. And x to the 0th are the constant terms over on the right. All right, so we've got all this. It's a little cluttered though, so I'm going to go ahead and get ourselves a clean paper or clean slide. We'll write this out. I'll write this out again, but without all of the notation so that we can see how the algorithm actually flows. All right, so we have our divisor 4x cubed plus x plus 1. We have our dividend 2x to the fifth plus 10x to the fourth plus 0x cubed minus x squared plus 0x plus 12. Just going to double check real quick, make sure I didn't miss any of those. All right, and then we're going to have our columns. I'm going to draw them a little bit lighter this time. Okay, so now we've got a big polynomial dividend and then our polynomial divisor here. So at each step, we compare the leading terms and we ask, what do we have to multiply by? By the leading term of the divisor to get the leading term of the dividend. So what we're going to do is we're going to compare the leading terms. Now the leading term of the divisor is always going to be the same as we go through this process. It's always going to be 4x cubed. the leading term of the dividend is going to change as we do our multiplication, subtraction, bring down, multiplication, subtraction, bring down, and so forth and so on. In this first step, our leading term is 2x to the fifth. So this is for step 1. And then we ask, what do we need to multiply by 4x cubed to get 2x to the fifth? Another way of thinking about it is we're dividing 2x to the fifth by 4x cubed and seeing what we get. So first of all, we want to look at the degrees. We want to say, what do we have to multiply by x cubed in order to get x to the fifth? And we've got a difference of 2 here. So we're going to be multiplying our dividend by an x squared term. So the first term in our quotient up here is going to be an x squared. But that's just looking at the powers. Next, we have to look at the coefficients. Next, we ask, all right, what do we have to multiply by 4 in order to get 2? Or, in other words, what's 2 divided by 4? 2 divided by 4 is 1/2. So we get 1/2 x squared, and that's because that's what you get when you divide just the 2 leading terms together. So 1/2 x squared is going to be the first term in our quotient. Next, we need to take the term we just wrote down in our quotient, multiply by our divisor, and write that down underneath the dividend. Now, because these are polynomials, this multiplication is more complex than it is with numbers, but if you do it term by term, it makes it easier. So 1/2 x squared times 4x cubed becomes 2x to the fifth. That was the whole point, to get the leading term of the dividend to match the leading term of the divisor. And then we go to the next one. All right, well, what about 1/2 x squared times x? 1/2 x squared times x is 1/2 x cubed. And you need to make sure that you keep it in the right column. So before we had an x to the fifth term, we put that in the first column under the previous x to the fifth. And then we multiplied 1/2 x squared by x, and we got 1/2 x cubed. Now, if we hadn't included all the terms in our dividend, we wouldn't have any place to put this term. We wouldn't have any place to put 1/2 x cubed, but we did, so we do. So 1/2 x squared times x is 1/2 x cubed, and then 1/2 x squared times 1 is 1/2 x squared. All right, so we found our proper term in the quotient, multiplied by our divisor, got our product down below. Now we need to subtract. And this is the step that often trips up students when first working with this algorithm. You need to make sure that you are subtracting every one of these terms. This subtraction, this red minus that's on the outside, notice it's on the outside of parentheses, and I've very deliberately done that to remind us that this negative applies to the 2x to the fifth and the 1/2 x cubed and the 1/2 x squared. We need to subtract all of them from the terms that are immediately above them. So when we do this, 2x to the fifth minus 2x to the fifth is 0x to the fifth. All right, that's great. We don't usually write that down because if we've done our job right, they cancel out, so we don't need to write them again. Now, at this point, we do have to go column by column, and so the 10x to the fourth term in the dividend doesn't have any like term subtracting it within the red parentheses, so it just comes down. 10x to the fourth minus 0 is 10x to the fourth. And then we've got 0x cubed minus 1/2 x cubed gives us negative 1/2 x cubed. And then negative x squared minus 1/2 x squared gives us negative 3/2 x squared. Now we bring down the remaining terms. And this is important here. We don't have to worry about this all the time when doing division of numbers, but when doing long division of polynomials, you want to be bringing down all your terms every time. So that was one step of the process. Now we keep going. At this point, we want to say, all right, what do we have to multiply by 4x cubed, the same leading term in the divisor, in order to get 10x to the fourth, the new leading term down in the dividend. So in step 2, we're comparing 4x cubed with 10x to the fourth. First of all, we see that we would need to multiply x cubed by a single x in order to get the powers to match up. And then in order to multiply something by 4 in order to get 10, we need to multiply by 10 over 4, or 5/2. So we have 5/2 x is equal to 10x to the fourth over 4x cubed. And so that's where we get our next term in our quotient. In this case, we'll put a plus between them because that 5/2 is positive. And therefore, that's what we want to use. Again, we're going to take this and we're going to multiply it. And we're going to get another polynomial down here to multiply. So 5/2 x times 4x cubed gives us 10x to the fourth as designed. 5/2 x times x gives us 5/2 x squared. Make sure to put it in the right column. And then 5/2 x times 1 gives us 5/2 x. All right, we multiplied, brought it down. Now we're going to subtract again. Now doing that, let's see, negative 1/2 x cubed just becomes negative 1/2 x cubed. Negative 3/2 x squared minus 5/2 x squared becomes negative 8/2 x squared, which is negative 4x squared. 0x minus 5/2 x squared becomes minus 5/2 x squared. And then 12 minus 0 is still just 12. Oh, that did not work. Sorry about that. Let me do that properly. Just trying to make sure we're not too crowded here. All right, so that was step 2, and we keep going. And we keep going as long as we can find a polynomial term that will make the first step work, multiplying by the leading term of the dividend in order to get the leading term of the divisor. The leading term of the divisor is now negative 1/2 x cubed. So we ask, what do we need to multiply by 4x cubed to get negative 1/2 x cubed? And this time, we don't have to multiply by any x's at all, but we do need to multiply by a number. In order to get from 4 to negative 1/2, we need to multiply by negative 1/8, which you can also get just by taking negative 1/2 and dividing by 4. We go through the process again. We found negative 1/8. We're going to multiply that by the divisor and see what we get. Negative 1/8 times 4x cubed gives us negative 1/2 x cubed. Then negative 1/8 times negative x gives negative 1/8 x. Oops, put that in the wrong place. That's why you need to be careful about your columns. And then negative 1/8 times 1 is negative 1/8. And once again, we subtract. And this is the place where you have to be the most careful about the subtraction when you've got negatives showing up. So negative 1/2 x cubed minus negative 1/2 x cubed is going to be 0, because the negative and negative become a plus. We got negative 1/2 plus a half, that's 0. Then negative 4x squared, this becomes negative 4x squared. Negative 5/2 minus negative 1/8 is negative 5/2 plus 1/8. Negative 5/2 plus 1/8 turns into a negative 19/8. And then finally, we have 12 minus negative 1/8, so that's 12 plus 1/8, and so that'll be 97/8. All right, so now we would say, can we do any more? We've got this term negative 4x cubed, and we ask, is there anything we can multiply by the 4x cubed of our divisor in order to get to negative 4x squared? And the answer is no, not while sticking with polynomials, which is what we want to do. The negative 4x squared that we've got here is not a multiple of 4x cubed because its degree is lower. Once your divisor comes down and becomes something that is of lower degree than the divisor that you started with, what you have found is your remainder. And what's happened up above? Up here, you found your quotient. So the remainder and quotient can be read off of this tableau just like they can be read off of the tableau for division of numbers. So in this case, the remainder is negative 4x squared minus 19/8 plus 97/8, and the quotient is 1/2 x squared plus 5/2 x minus 1/8. Let's write those down and explore some of what that means, some of the different ways that we can express that. And I'm going to go back and forth here a couple times just to make sure that I copy everything down correctly. So let's see, we had the dividend was 2x to the 5th plus 10x to the 4th minus x squared plus 12. The divisor was 4x cubed plus x plus 1. The quotient that we got was 1/2 x squared plus 5/2 x minus 1/8. And then the remainder was negative 4x squared minus 19/8 x plus 97/8. Negative 4x squared minus 19/8 x plus 97/8. All right, so what does this mean? A number of different ways that we can write down what this means. This means that 2x to the 5th plus 10x to the 4th minus x squared plus 12 is equal to, the dividend is equal to the divisor, 4x cubed plus x plus 1, times the quotient, 1/2 x squared plus 5/2 x minus 1/8, plus the remainder, negative 4x squared minus 19/8 x plus 97/8. Furthermore, this is the only way to write down the dividend as in terms of quotient and remainder with this divisor, if you require the remainder to be of lower degree, or essentially the only way. With only minor cosmetic changes to the way that it could look. Possibly more interesting to us is the following. If we were to divide everything by the remainder, not the remainder, but by the divisor, what we could get is that 2x to the 5th plus 10x to the 4th minus x squared plus 12 divided by 4x cubed plus x plus 1 is equal to the quotient 1/2 x squared plus 5/2 x minus 1/8 plus, and now the remainder, negative 4x squared minus 19/8 x plus 97/8 divided by the divisor, 4x cubed plus x plus 1. And so this gives us another way of writing down a rational function. If we have a rational function where the degree of the numerator is greater than the degree of the denominator, we can use this process to write it down as a sum of a polynomial plus another rational function, but this rational function has the degree of the numerator being less than the degree of the denominator. So we can use this process of long division of polynomials to take any sort of improper rational function where the degree of the numerator is higher and write it as a sum of a polynomial and a proper rational function where the degree of the denominator is lower. Now, one thing that you'll notice is that the degree of the polynomial that we get is equal to the difference of the degrees that we started with. We started with a degree 5 polynomial over a degree 3 polynomial. We got a degree 2 polynomial out of it. That's not an accident. That's exactly because 5 minus 3 equals 2. Another way of thinking about this, and the way that's relevant particularly to us as we look at slant asymptotes, is that when x is very, very large, the proper rational function over here is going to be very close to 0. And that's because the degree of the denominator is greater than the degree of the numerator. If x is huge, then the x cubed in the denominator of this fraction will be much, much bigger than the x squared on top. And so the denominator of this term is going to be huge compared to the numerator, which means the overall fraction is going to be tiny. What this means is that when x is very large, the rational function on the left looks a whole lot like the polynomial on the right. And in fact, this is always true. Given any rational function, when x gets very, very large, as you look at the end behavior, eventually it will start looking like a polynomial. It will start behaving like a polynomial because this extra remainder over divisor part from the algorithm will essentially disappear. It'll just become 0 because the denominator is so much bigger than the numerator. So that's the technique of using the long division of polynomials. What does it matter for us? So when f of x equals, I'll write it as a of x over b of x, again, is a rational function, and the degree of a of x is equal to the degree of b of x plus 1, the slant asymptote of f has an equation given by the quotient of a of x divided by b of x. So when the degree of the numerator is exactly 1 greater than the degree of the denominator, then when you use long division of polynomials on them, you're going to get a degree 1 polynomial left over. A degree 1 polynomial is exactly a line, and that line will be precisely the slant asymptote. And the reasons for that are exactly what we just said. The remainder will be something that gets very, very small as your values of x get bigger and bigger and bigger, moving towards the left or the right. So finally, let's do an example. Let's find the vertical, horizontal, and slant asymptotes of f of x equals x squared, 3x squared plus 6x plus 30 divided by x minus 6. All right, so first thing, of course, that we would want to do is to factor this, make sure that we've got all of our cancellation done. So we factor, and we get that f of x is equal to 3x squared plus 6x plus 30 over x minus 6. We can factor a 3 out of the numerator and get x squared plus 2x plus 10 over x minus 6. And you'll notice that the numerator here doesn't factor any further. In fact, if you go and you use the quadratic formula to figure out where the zeros are, you'll find that this actually has no zeros. So in particular, there's no cancellation to be done between the numerator and denominator. So let's see, vertical asymptotes, in this case, is pretty easy. We've only got the one term in the denominator, which will generate a vertical asymptote for us, and that vertical asymptote will be at x equals 6. Horizontal asymptote, well, we've got none. Because the degree of the numerator is higher than the degree of the denominator, there is no horizontal asymptote. However, because the degree of the numerator is 1 greater than the degree of the denominator, we have a slant asymptote. Let's find it. So we are going to use long division of polynomials like we did before, and we're going to take the numerator of the polynomial and divide by the denominator. You can remember that because it's the same division as is being implied by the fraction form of the function to begin with, top divided by bottom. So now let's go through this. The good news is that when you are working on a function with a slant asymptote, you'll actually only need to go through the process of multiplying and subtracting once, rather twice, rather than the 3 times we had to in the previous problem. So we say, what do we have to multiply by x, the leading coefficient, the leading term of the divisor, in order to get 3x squared, the leading term of the dividend? In this case, in order to get from x to 3x squared, we have to multiply by 3x. And notice I'm putting it over the x term that already existed in the dividend. So now we take 3x times x minus 6, and we get 3x squared minus 18x. And now we'll subtract. So 3x squared minus 3x squared is just 0. We don't bother writing that. Then 6x minus 18x gives us positive 24x. So now we say, all right, well, what do we have to multiply by x in order to get 24x? And the answer is 24. So we take 24 times x minus 6, and we get 24x. Then 24 times 6 is 144, so that's minus 144. We subtract, and we get 0, and 30 plus 144 is 174. Now, as we did last time, there are lots of things that we can say based on this. We can say that, well, 3x squared plus 6x plus 30 is equal to x minus 6 times 3x plus 24 plus 174. Or we can rearrange that in a number of different ways. But for our purposes, we just care about the quotient. We just care about this up here. This linear polynomial expression is precisely the formula for the slant asymptote. So the slant asymptote for this function has the form y equals 3x plus 24. And that's how we can find the slant asymptotes. Now let's actually try and graph this out. As much as we can. Let's see. Let me go ahead and make my tick marks be worth 4 each, going up. And then we'll just use standard. Yeah, 1, 2, 3, 4, 5, 6. 6 is the point that we really care about the most. Okay, so we have our grid here. Let's sketch in what we have. We know that we've got a vertical asymptote at x equals 6. So we'll graph that. And we know that we have a slant asymptote of y equals 3x plus 24. So that is going to have a y-intercept at 24. So at this point, graphing the slant asymptote is just the same as graphing any other linear function that we've done. And so it's got a slope of 3. Now, 2, 3. Because I'm scaling things a little bit weird here, let's say that I know that if I go over 4 on my horizontal axis, then that means that I'll go up 12 on the vertical one because the slope is 3, and so the vertical change is always 3 times the horizontal change. So if I go over 4, I'll go up 12. So at this point, 4, 36 is on my slant asymptote. Now I'm going to try and sketch that out nicely. All right, so here's what our slant asymptote looks like, approximately. Yeah, let me fix that. Okay, so that gives us some insight into how the graph is going to look. Let's see if we can figure out a little bit more. Remember that f of x was equal to 3x squared plus 6x plus 30 over x minus 6. Let's see if we can get a few more points in order to figure out what the graph of this looks like. Let's figure out the y-intercept. If f is 0, then we get 3 times 0 squared plus 6 times 0 plus 30 over 0 minus 6. So f of 0 is 30 over negative 6, which is negative 5. So that means that the y-intercept is going to be somewhere down here. So it's going to be at 0, negative 5. As we mentioned before, we've got no x-intercepts, no zeros. So let's just get a couple more points in order to figure out what this graph looks like. So let's take f of 7. Let's see what's happening on the right-hand side of the graph. F of 7 will be 3 times 7 squared plus 6 times 7 plus 30 over 7 minus 6. So 7 squared is 49. 3 times 49 is 147. 6 times 7 is 42. And we got 30 all over 1. So 147 plus 42 plus 30 will be 219. So we have clearly a very, very tall graph here that's going to stay pretty high up there. In particular, note that it's above the graph of the slant asymptote. What this means is that the graph of this function doesn't look quite like the graph that we sketched before, but instead looks something like the following. Up here at this stage is going to do that, although it's not going to come nearly that far down on the graph based on what we just sketched out, and it's going to do something like this. So it's going to fit in between the asymptotes in this sort of way rather than in the broader way that functions can do sometimes. But this one just happened not to. So this is how a slant asymptote works for a rational function whose numerator has degree exactly one more than its denominator. Once you do the long division of polynomials, graphing the slant asymptote is simply a matter of graphing the line given to you by the quotient of that long division of polynomials. There is one last topic in graphing rational functions that we need to address, and that's what happens when you do have a common factor in the numerator and denominator of a rational function. All right, so let's take the topic for this, is missing points. Let's take as an example f of x is equal to x minus 2 over x squared minus 4. Let's look at this function and say we want to try and graph it. Well, if we factor it, we get that the numerator is just x minus 2, nothing to do there, and the denominator is x minus 2 times x plus 2. Now remember, importantly, we said that in order to calculate the domain, you have to look at the factored denominator before doing any cancellation, and this is why. So now when we look at the domain of the function is going to be all numbers other than 2 and negative 2. Because 2 or negative 2 would make the denominator equal to 0. Any other number won't, and therefore any other number is in the domain of this function. However, in the next step, when we go on to try to find intercepts of the function and asymptotes of the function, we need to work with the reduced or simplified form. The only thing that we use the unsimplified form for is the domain. So now we simplify, and we get, if we cancel, whoops, not that one, we get 1 over x plus 2. And now to determine the zeros of this function, the asymptotes of this function, the intercepts of this function, all these things, we use this simplified form. So we can figure out that there are no x-intercepts, because you can remember that the x-intercept comes from where the numerator is equal to 0, and the numerator of the simplified form is never equal to 0. So we have no x-intercepts. Our y-intercept is what we get when we plug 0 in. So our y-intercept is at the point 0, 1/2. All right. We have a vertical asymptote, which we can see based on the denominator. We can see in the simplified form that if we plug -2 into the denominator, we'll get 0, and so that's going to give us a vertical asymptote. And then we can see also the horizontal asymptote. This simplified function has a degree of the denominator of 1 and the degree in the numerator of 0. Therefore, the degree in the denominator is greater, and the horizontal asymptote is y equals 0. So we can graph out what this function looks like without too much trouble. We have a vertical asymptote at -2. We know that we've got a y-intercept at 1/2. Go ahead and do that in red. We know that we have a horizontal asymptote at 0. And all these things together allow us to graph out the function. A sketch of it. Now, we're not quite done. And the reason is that the graph as I've sketched it out now isn't correct. And the reason we can see it's correct is by comparing the domain of the red graph that I've sketched with the domain of the function. We know, based on what we did right at the beginning, that the domain of this function is all real numbers other than 2 or -2. Now, the fact that -2 is not included in the domain of this function is shown in the graph. The graph has an asymptote at -2. There are no red points on the graph that sit immediately above or below -2 on the x-axis. There are no... if you just looked at this graph, you would conclude that the domain does not include -2. However, according to the graph, it looks like this function does include 2. Look, we've got a point right there. We got a point on the graph that has an x value of 2. And yet, if you tried plugging 2 into the original function, you'd get something undefined out of it. If I tried plugging in f of 2, I'd get 2 minus 2 over 2 squared minus 4. I'd get 0 over 0, which is undefined. So we really shouldn't be able to put a point in there. It looks like we've got 2, maybe 2 comma, maybe a fourth, and having that point on the graph suggests that f of 2 is a fourth. But that's not the case. F of 2 is undefined. 2 does not belong to the domain. What happened here is that our simplification process lost us information. The original function had some information that for many purposes was redundant, which was why we simplified it. However, it is still important, which is why we don't forget it. What you need to do every time you go through a problem, you need to check to see whether you whether your graph needs to have any missing points. This graph should look like the following. There should be an open circle right there. And what that indicates is that we have a hole in the graph. The graph of the function contains all of the other points on the curve very, very nicely, but this one specific point isn't included. This one specific point in the graph shouldn't be there because it's not, the x-coordinate of that point is not in the domain of the original function. So what causes this to happen, what causes holes in graphs to happen, is when you have factors in the denominator that are all canceled out when you go to your simplification process. Whenever that happens, you need to put a hole in the graph in order to represent that, that point isn't actually on the graph of the original function. It's only on the graph of the simplified function, and that's because we forgot some information when we went from the original function to the simplified one. Now, this isn't at all to say that you shouldn't simplify the functions. You absolutely should. In order to compute asymptotes, end behavior, all these sorts of things, you absolutely do need to simplify your function. But whenever you do that, you need to go back and make sure that the domain of the graph that you've drawn matches with the domain of the function itself. And if you've canceled any of your factors in the denominator, you need to take care of that. And you need to include a hole there. Now, this only happens when a factor disappears completely from the denominator. Sometimes you'll have a repeated factor in the denominator where some of the factors are canceled, but the factor still remains, in which case you'll get an asymptote at that point and you won't have to worry about it. You only need to worry about it when there are certain factors that disappear entirely from the denominator when you go through the simplification process, like the x minus 2 factor did here.